be achieved with high levels of frustration, in the sense that the more point defects you have, the more frustrated the system will be. And then I would like to, this is the message for this part of the talk. And I would like to talk to you now about a few related things that we have done in 3D now, and related tubes, like this tube that you see over there. And we wanted to go beyond not just kinematics, but also look at the elastic deformation of the system. And that's when we got the idea to do the Merlin software that I am going to show to you. That is a simplified model that we consider only panel shear and stretching, okay? As you can see here, the bending of the panel, okay? Like if this is a panel, then how it's going to bend, and the bending of the folds, only these three deformation modes. What is very nice about Merlin is that it is a bar and hinge model. It's very efficient, okay? And today I visited Professor Oscar class in FEM. If you try to do this in FEM, even with all the skills that you have, and try to model a tessellation like this in FEM, just generating the mesh will take a long time. And with Merlin, we can do this rather quick. And of course, the FEM can provide us, if it's well done, much more details than Merlin. Merlin is a reduced order model, simplified, only the three deformation modes, but can give a lot of insight into the behavior. And here is the history. This idea started with Schenck and Guest in Cambridge, and then we worked on it and implemented several other things, as you can see here in the slide. And essentially, this allows us, for example, to build the stiffness considering panel shear and stretch, for example, bending, and express the folding as a function of the bending and stiffness. And a lot of the work in origami is based on a rigid origami like this, then where the panels do not deform. But if we do bending, for example, then we are going to have a very high non-rigid origami, as you can see here. And again, the point is that with FEM, doing this type of simulations can be very time-consuming, okay? And then we have basically two basic elements in Merlin. The simplicity is very important. And then we use a hyperelastic constitutive model for the stretch. And then we have a strain energy function here. Do one derivative, get the stress, another one, you get the modules. And since this is just a bar, right? These are not tensors, these are all scalars, right? And this will give me all the information that I need to build the finite element matrices and implementation, considering both material and geometric nonlinearity. And a very important behavior is the behavior of the rotational springs. And here we use a similar approach as before with a strain energy for the rotations, and then we do a derivative, get the moment, another derivative, get the tangent stiffness, and we introduce some penalty here close to 0 and 2 pi, because with origami we need to be able to capture the angles when the dihedral angle is 0 and 2 pi. They are totally different, and we need to capture the entire range, and this allows us a simplified way to take care of contact with these barriers at close to 0 and 2 pi, and then I can go and build the internal force vectors and build the stiffness matrices. And one idea in origami, because we need to take care of the entire range of deformations, is to have a unique way to define the angles and then in many different ways. If I just use, for example, here in arc cosine to define the angle, it's impossible to differentiate between the angles between 0 and pi and 2 pi. And but then I can have a sine indicator that will help me, but then there is a discontinuity here. But if I include the mod of 2 pi, then I will have a unique way to define the angles. And this is very important because this will allow me to treat deformations from very small angles to very large angles. And when we do this, Bill, how much time? 10 minutes, okay. I'll try to quickly, when we do this, then I have to do the derivatives, right? Then when you do derivatives using a standard formula, then for example, you are going to have trigonometric functions in the denominator. And this thing is going to go up. The limit may be finite, but the computer does not know. And we get theta here equals 0 or pi, this is going to blow. So what we did was to use vector and tensor functions and rewrite this without any trigonometric functions. As you can see here, this final expression. And we can also do this for the stiffness matrix and the Hessians, the second derivatives. And then in Merlin, then there is no trigonometric functions. Everything is written in terms of vector and the distance functions. And we use a similar scheme to the arc length to solve the problem. And then we can solve very complicated problems. For example, like this one that shows the mural or it pops through. For example, if I have a tessellation like this one, and I apply a force here, then you can see that this will change locally the entire configuration. And then we can quickly simulate this in Merlin, okay? And here is, I am hesitating if I should do, thinking if I, just to show you, just for you to see how long this takes to run. We seems you cannot see my screen, right?
We see you. I'm not sure online we can see your screen.
It's okay. I can skip this. I can skip this. You can just trust me. It's very fast. Okay, that's what I wanted to show you. It's really, and maybe here I am running it. Probably you can see it in the online, right? So I already finished this simulation. Okay, and all right, but I will go back so that.
Looks like a blue screen.
I think it's here. Maybe I will stop and start sharing again.
It's because you shared a window instead of a screen. So
Okay, this would be good. Yes, thank you.
but it's not.
So this one is okay.
Yes.
All right, so then as I indicated to you, we wanted to look at the behavior of the tubes, and we wanted to find a mode that is very flexible, that would allow deployability, and other modes that would be much more stiff. Then we started to look, for example, at the band gap of the eigenanalysis between, for example, the first two non-zero eigenvalues. And then when you look here at the sheet, that is essentially this kind of configuration, you can see that this is very floppy. And as you can see here, the eigenspace, eigenvalue versus the extension is not very clear. And you have, you don't have anything clear, and even this band gap is very small. And then we started to look at the tube that seemed promising. But then we looked at different configurations. For example, we started to look at the align configuration that you see here, the internal coupling, and finally the zipper coupling. Let me see if this will work. And then, as I am showing here, for example, this is the zipper tube. And then if I put two of them like this, you can see that they are aligned, okay? You can see here that they are quite aligned. And then this is one configuration. The other one is when you put another tube inside, but then this is the one that I will show you on the slide. And finally, another one is that if you have it like this, and then if you rotate like this, you are going to form what is called the zipper tube, okay? That then will allow you to have very interesting properties. And even as I demonstrate here, see, I am just touching one end, and you can see here that this axial mode is very flexible, right? And all the other modes, bending, twist, is very, very stiff. And this let's go back here. Yeah, this then we have these three configurations, and then we start to look at, for example, the band gap in each case. And we could see here that the zipper had really a very nice property, because this first mode here seemed very low energy, and all the other modes, okay, very high energies. And this allows us a deployable configuration. This paper is this idea is summarized in this paper in PNAS. And very quickly, just to take a look here, this is the energy distribution using materi. As you remember, when we have three deformation modes: stretch, bending, and folding. And you can see that all the energy in the deployable mode is in folding, okay? And in the higher modes, then we engage bending and shear and stretch, as you can see here. And the deformation in the first mode is just a fraction of the other deformations. And then you can see here the energy profile. And here in the higher modes, you have a lot of bending and shear. And that's what explains the behavior of this pattern. And then what can we do with this? For example, we can explore cellular assemblages so that we can look at ideas like self-assembly, deployability, tunability, and so on. And then if I arrange the pattern in this way, align in one direction, zipper in the other, then I get a multi-configurational material system with an infinite number of configurations. And you can see that, for example, in the XY plane, it is auxetic. And here, the stiffness versus extension, we can see that in the X and Y directions are quite soft for a long region. And in the Z direction is very stiff, as you can see here. And there is an instability here. And you can see the instability right here, because what happened is you can see that there will be a situation here, I don't know if you can see, where these panels will be totally aligned. And then as the deformation continues, it has to decide if it goes left or right. It has to decide if it will go this way or if it will go this way. Make sense? Is it clear? Okay. And that's that instability point over there. And then we can choose one configuration, for example, that let's say I don't do a configuration somewhere. And then, for example, we can freeze this configuration and we study it and see if it satisfies some of the properties that we would like. And for example, what else can we do with it? For example, we can do an interlocking system that is being illustrated over there. And here is the interlock system. It's a multi-scale structure. Maybe this could be a building of the future. This has the global structure here, the cellular configuration here. And pay attention how big this is, but this is flat foldable. Okay? And for example, if there is an emergency, for example, we can have a deployable structure that will be a bridge made with this. And then you can see that the bridge can support a lot of load. And this is the prototype that I am here showing you in the deployment. And this is the bridge. Okay? This is the bridge. And flat foldable. If the thickness were 0, then it would be totally flat foldable, but the thickness is finite. And finally, the final idea I'll mention to you is I wanted to explore the idea of scales because we did this, for example, meter scale, as you can see. And then the idea is, can we do this at the micro scale? For example, can we do this the size of our head? Because then we can explore this for applications in micromechanics, multifunctional systems, multifunctional materials, and so on. And this would be very interesting. And for example, you can see that this looks quite big, right? But this has a finite thickness, but this is the zipper that I just explained. And this axial wall has very low energy, and pay attention now. Not so big. So, and then what happened is we did this study, and then we did this. This here is about 30 microns. No, 100 microns, right? Because 30 is the scale bar here. Is about 100 microns or so. And this was printed at Northwestern in collaboration with Civilengineering and Glaucio. And they used the two-photon polymerization technique on a nanoscribe machine. And we are very fortunate that we just got this machine at Princeton, and we intend to use it over there. And we did some in situ SEM mechanical testing, as illustrated here, to investigate the anisotropy, different directions, give very different stiffness, and also the material properties. This material is the DIP, viscoelastic, then we modulate load, as you can see here. And then if we test in the X direction, you can see it's more or less an elastic material that has a plateau, will flow. And what is very interesting on this, if you look at the numbers here, we start here, and then you can see that around 5, for example, there is a tremendous deformation, but as we remove the deformation, as we unload the specimen, and it recovers almost the original configuration. And that is a very interesting property. In this direction, for example, we are going to have a hardening behavior. And I will also, we can explore some change of Poisson ratio at the micro scale, and we did that. And further details about this work you can find in this paper here published in the journal Small, that shows very large degree of shape recoverability, anisotropic properties, and reversible objecticity. And then just summarizing, we have seen since the beginning, we have seen improved bar and hinge models. We have seen metamaterials that are done by exploring origami reconfigurability and frustration at the unit cell level, tessellation level, material level, and we can achieve a structural tuning through reconfiguration. The triclinic system seems very interesting to do architected programmable materials. And also something that points to the future for us is that origami has a lot of regularity, allow us to look at architected ordered materials, but also we can restart the ordering and look at the irregular architected materials. That's the summary of what we have seen today. Thank you very much.
Thank you, Glaucio, for an excellent presentation. I want to first, before we go to the questions in the audience, Professor Gardoni, is Professor or Dr. Ken Chong is online. And Ken, could I ask you to join us and ask your question directly of Professor Paulino? Ken Chong was a program manager at the National Science Foundation with Professor Paulino. So Ken, can you join us?
Yes, thank you, Glaucio. Really enjoy your talk. Actually, I also have some encounter with this kind of engineering. After I got my degree from Princeton in the 70s, I worked in a building system company, National Steel Corporation. And I was promoting a kind of connection which consists of some kind of a male and female type of connection, very similar to your what you presented. Later, when I was a program director at National Science Foundation, we sponsored some projects at MIT on deployable space structures. And you probably know of it. But all these projects didn't have the mathematical rigor and elaboration that you presented. So I'm really glad to see that. I have one question though.
Yes.
Looking at this kind of structure, which can withstand tremendous deformation, and it could have some applications in seismic engineering, which is very dear to the late Professor Newmark. So I was looking into this problem too. I was using some kind of a cloaking of the seismic wave to do that, but that was very difficult. I think your structure may be more promising. Can you comment on that, Glaucio?
Yes, Ken, I can. Actually, you are reading our minds because I did not show anything, but this is a new research project that we just started, not funded by anyone, just out of curiosity, because we got the same idea that you did, Ken, that this kind of tessellations that I have just shown, either ordered or not ordered, they could be excellent for cloaking and invisibility, not just related to earthquake, but for wave propagation, wave guides, and wave protection. And then we are, I cannot give you any result at this point, but we are planning to do some theoretical studies and also some experiments to investigate this idea, if it makes sense or not. I think it does. I don't have any results at this point, but maybe if we get successful and this successfully done, maybe Bill could invite me to come back again, and then I can share that.
Of course. Thank you, Ken. It's great to see you, and we hope to see you on campus again sometime soon.
And Ken, maybe another comment, since you mentioned your interest, this idea I think is really quite fascinating, and also it relates quite nicely to the Nobel Prize in Physics in 2016 on topological protection and the topological phases of matter. And actually one of the professors that won the Nobel Prize, Duncan Haldane, is a professor at Princeton. And this is something also that we intend to look the insensitivity to defects so that we can protect if there is an important piece of component or structure that needs to be protected, then we could engineer the origami and so that the waves can be tailored to achieve that protection system.
Glaucio, if I may follow up, you are a member of the NAE, so every year you come to Washington, right, for meetings. So next time, if you have some time, I'd like to invite you to George Washington University.
My pleasure.
Give a distinguished lecture.
My pleasure, Ken. Thank you very much.
Thank you again, Ken. I'd like to turn to Professor Gardoni. He raised his hand at the beginning.
That was a great presentation for a very interesting topic. I had a question you called accessibility, and more of an opportunity for you to tell us a little more. So what you presented today is for a perfect configuration. But of course, during the manufacturing or temperature effects, the vertices may move, the configuration could change. Can you comment on the impact of perfection on the origami?
Yes, and Paulo, as a disclaimer, I would like to mention that everything that I can tell you can be found in this page. Okay. Transparency in the oil society. As you correctly pointed out, there is a big influence on the small and imperfections in our there is the national peers, and there is also very important here, so that I could learn from you. And we could collaborate in this work. And I think this work was one of the very first to really provide a mathematical framework to do this kind of analysis. And as we have shown in this paper, this is extremely important. In the presentation I gave, we did not consider that, but that does not mean that we do not intend to do that. And for example, even for example, one area. But since everything I talked here was more or less quasi-static, then this tends to be very forgiving. But for example, for the work related to the question that Ken asked, when we are going to have not just the space problem, but also the wave propagation and the time domain, the wave propagation, then small imperfections will impact not only the actual behavior, but the wave properties and the wave propagation. We believe that in that work, this will be something that this paper is very interesting. And again, thanks for the opportunity to learn from you and to collaborate.
Correct.
Glaucio, very nice talk. Really enjoyed it. I have a question regarding the way you presented two modes, the ruler mode and box mode, and very nice analytical expressions for Poisson ratio, positive and negative. And if you look at that expression, it's a length scale in there. So, and there's some kind of a length scale in those expressions. So my question is, if we take that pattern and start making it at a smaller scale, bring it down. So our Poisson ratio has now a length scale of a microstructure, right? Now, if I link that part towards the last part of the talk, you're going to get this machine which is going to do 3D printing of that microstructure. So now your microstructure is done, but you have a very nice elegant analytical expression for positive or negative Poisson ratio. Now, I did that thing and I want to build a structure B on which I'm going to do a bending test. And that beam is made of the material that you're making out of your 3D printing. So if I take that Poisson ratio, which has a length scale at the microstructure level, and now plug it into momentum balance equations. Momentum is sigma, and now our sigma has Poisson ratio, which is actually Poisson ratio for metal. Do you see that thing will give us results as we expect from continuous gradients, because continuous gradients may not have that 8 points where they will flip over from positive to negative. And when you plug it into momentum balance equations, what kind of issues you can see?
Some questions, but my understanding is this. What I have shown is, well, and allow me to finish the answer completely, because I'm going to say something a bit more at the beginning, but then I will explain. What I have shown, the analytical derivation, they are valid for any state. Okay? However, they may be correct, they may be incorrect. Because everything I did, I was only able to derive the analytical expressions, Civilengineering. Anytime, for example, if I have, whenever we are in the finite deformation range, like what I did, we did with Merlin, for example, then those analytical expressions, they are not applicable, because I was only, not only all the researchers in the group that I know, the group at Harvard, France, and so on, they were only able to do the derivations if you consider linear behavior, okay? Again, they are valid at the end scale. What happens? In the finite scale, as we did the experiments, and I showed you the experimental results, that look like even sometimes I was joking with my collaborators, once we figure out how to do the fixture of, before the fixture, the results were not separate. They because we didn't have a good reason to do the test. But the way I showed you the results are real tests. Okay. However, when we start looking at us, then other things, other physics will come into the problem. Then maybe if we keep going with smaller and smaller, for example, then let's say weak forces, forces of adhesion, and so on. For example, this scale, I think the most difficult thing is that. And it took us a long time to understand what gravity does with this. If I am mini-quantizing, gravity doesn't matter, right? But other forces will. And then, for example, to go and look, for example, let's say a closed loop system, a thermodynamic system, and do the complete study of the mechanics is something very, very important. And it will also depend. I don't like this with the printers very much because many times you don't print what you think you are printing because the printing process is a very dynamic process. It involves many things, temperature, sometimes light. We are printing this problem, and especially when you miniaturize things, there are defects and effects of what Paul said that comes into the picture. Then these are things. Origami engineering is a new area of research. But your question is excellent. I think this would be a fantastic topic for a proposal. You will collaborate. Thank you.
Glaucio, thank you very much for very engaging and inspiring lectures, as always.
Thank you.
So as Professor Spencer mentioned in the beginning, you have done a lot of work in fraction mechanics as well. So I was wondering if you had thought about combining that work with this work in origami. For example, is there a origami pattern that will lead to a more fracture resistant structure, one that will lead to a less of the cracks, that requires more energy for the crack to propagate? If I make use the same material to build two structures, which origami pattern should I choose if I want the highest resistance for fracture propagation?
Well, among the great questions, and I am very sorry to disappoint you. I do not have an answer for any of the questions you asked. As you could see here, I never considered fraction in this work. I think it would be very important to consider. And especially, for example, things like fraction fatigue. If we go, most of the things here we're going with paper. Suppose that you are going to do an actual extractor that will be deployed in space, or you are going to use metals, for example. And then considerations about strength, fraction, and so on would be very, very important. I have not done any of them.
So let's open some opportunity for future research.
Yeah, but it is. I know that some colleagues, for example, they have done some experiments and some modeling, but basically we're not related to the questions that you asked. We're more trying to understand, for example, if they have a tessellation like this, they do a plate of metal. For example, they work by Zongbio at the University of Oxford, Yang Chen at Tianjin University. Then they were looking, for example, at fatigue behavior and also fracture behavior, but for example, is a crack, a pre-existing crack, and then apply some simple deformation states to see how that crack will impact the tessellation. But I would say there is much more to be done, like the questions that you asked.
Thank you.
Good.
I'm going to go to an online question and then we'll come back here. Professor Manny Gopalvarkar wasn't able to attend, but he congratulated you on an excellent lecture. And as you know, he's in construction management. And so he wants to know if there's research that is being done on moving from the paper version of these to the construction materials version that can actually be deployed in large-scale applications.
Yeah, that's an excellent question, Ronnie. And yes, there is actually what comes into my mind is there is a company in England that is called RoboFold, and they are trying to do exactly what you said, trying to translate some of these origami concepts into large structures, especially sculptures. At this point, that's what I have seen. And they are using robots to be able to fold the systems. And later, if you Google RoboFold, I think you will see some very interesting pieces of work right there. This is some of the work that I am aware of. But for example, there are also some work that is being done, for example, for shelters, because especially for emergency situation, if you have, for example, I had a student that lost his home, and he was from Honduras, and then was studying origami shelters because he said his family could have benefited from that. And also, for example, if you look, there is a company, a company in Minnesota, for example, that is not civil engineering, but they did a kayak that you can take with you, and then you can go to the lake, deploy, and then do the kayaking in the origami kayak. These are some of the things I remember, but yeah, these are one of the main difficulties that we have right now to bring the origami from the mathematics to the large scales is the thickness. Because what happened is, even the properties I showed, once you have thickness, all those things break down. They are all the mathematical proofs. If you have 1 million sheets, for example, the thickness is 0. But if you put 1 million sheets together, thickness is not 0. This will be finite. So, and the thickness accommodation techniques is one of the main areas of research in origami. And I think when we understand that better, okay, then I think there will be a lot of development. But the thickness accommodation is a very... And moreover, maybe just to conclude, and what also is a problem that many times for me, of course, I recognize the importance, but sometimes I have a little bit of difficulty to work in the problem because, for example, when I work in the things that I showed you and I consider the limit that the thickness go to 0, then I get very general results mathematically, and I love that. But when there is thickness, each case is one case. For example, there is a science paper written in a few years ago by Zhong Yu at the University of Oxford and Yan Chen. And for example, they looked at 5, 10 configurations with thickness. We have an infinite. And that's what needs to be done. Maybe some of the very bright students, you can get excited to work with thickness accommodation techniques so that we can scale up things and go to space and do big things.
For the people in the audience here, we're going to go up to the bridge and have a reception. And so I'm going to take advantage as the host of the this lecture to ask the last question, and then if we could ask you to come up and join us and talk with Professor Paulino directly. So, Glaucio, you just mentioned that there are many young people here, and they've got their careers ahead of them. So, as one of the exemplars of our field, maybe you could give them some advice on what it takes to be successful in engineering.
That's a very important and difficult question. I was not expecting that question, Phil. The advice would be based on the fact that you are at the University of Illinois. And one aspect, and I mentioned, for example, maybe I will give an example that will help me to answer. I visited Oscar class in finite elements and Shelley class in structural analysis. And I mentioned to them that the opportunities that they have here, that many times they take for granted, you cannot find that opportunity in too many universities. For example, here, something that is fantastic, you have the class in matrix analysis and finite elements, right? The one that I visited today, Shelley. And then Professor Oscar is teaching finite elements. And then we have, I think, Professor Massoud and Professor Duarte's classes in nonlinear finite elements, computational mechanics, plates and shells, and also probably Jeho is teaching finite elements for fluid mechanics. And for example, many universities, you do not have these opportunities. And then I would say, to be successful, try to benefit as much as possible the time that you are here. Doesn't matter if you are doing undergrad, master, or PhD. This university has so much to offer, but it will not come to you. Okay, you have to work for it, and then this will give you a very nice initial condition. When you live here, you may go to a national lab, you may go to the industry, you may do your PhD, but one thing that I admire here is the opportunity to learn the fundamentals well. What I believe, and this is what I apply to my life too, is don't cut corners. Learn the fundamentals very well. Then the derivative things, it's like me here, I'm working in Origami, but the reason I was able to do this, I believe, is because I tried to learn the fundamentals very well. That allowed me to learn this stuff by myself. And this is the kind of education and the kind of opportunity that you have here at the University of Illinois. Benefit from it.
Thank you, Glaucio. As a token of our appreciation and remembrance of this lecture, we'd like to present you with this this little icon. And so congratulations again on a great lecture. So with that, we'll close today's lecture and invite you to come up to the bridge and enjoy refreshments and to greet Professor Paulino yourself. Thank you.
Thank you. I think I messed it up. I'm sorry. I should not have. I messed it up when I tried to run the code. Yeah, I should not. I should not run the code. Sorry about that.
The only thing I can do is it's working fine now.
Yeah, more but thanks for your help. Thanks for everything.
A lot of people online. So you can see if there were questions.
Excellent.
Going on.
Much. Yes. Thank you. Wow. We'll see you. Nice to see you all.
I learned a lot. It was a lot of fun.
Thank you. Thank you.
Yeah. I think it's going to be so crowded up there. I can't say that I'll have a chance to see you.
It was very nice.
It was fun to have lunch there.
Yes.
Yeah.
Thank you all. Thank you very much.
So, Glaucio, I can't join, but I will join you for dinner.
Excellent. Then I'll see
I
you
will be a
around.
little late. Just
That's good.
So you're waiting only tonight. Okay.
Is there a problem?
What's that?
Yes, I'll see you.
I'm not planning to.
Michelle, you gave me good advice.
No problem.
No, but you should have someone
I'm a straight
that maybe you had decided to put your name on the second night and you forgot to remove it. But it is fine.